We are researchers from VN Karazin Kharkiv National University and Georgia State University. I am pleased to present our work titled A Neural Network-Driven Adaptive Approach for Maximum Coverage Location with Restricted Zones. The authors of the work are as follows: Sergiy Yakovlev, Yehor Havryliuk, Olha Matsyi, Andrii Hulianytskyi, and Alexander Kirpich. In the modern world, placement problems for maximizing coverage of a given area find wide applications in various fields such as logistics, urban planning, telecommunications, ecology, and defense systems. The classical maximum coverage location problem, MCLP, involves placing a limited number of facilities, for example, base stations, warehouses, or sensors to maximize the covered area or the number of demand points served. This is the maximum coverage location problem with restricted zones, and it appears everywhere: telecommunications, healthcare, ecology, and urban planning. However, real-world scenarios often introduce additional constraints, such as arbitrary shapes of the area and covering objects and restricted zones for facility centers. Here's what makes this challenging. We have an irregular area that needs coverage. We use n covering objects with arbitrary shapes, like ellipses. Each object can be positioned and rotated. Object centers cannot be in restricted zones. But the objects themselves can overlap with restricted zones to provide coverage. This is a continuous, high-dimensional, multi-extremal optimization problem. Our framework integrates three innovations. Component 1. Adaptive penalty mechanism. Instead of manually tuning the penalty coefficient erho, we treat it as an optimization variable. A neural network learns to adjust rho automatically, increasing it when constraints are violated, adjusting when optimization stalls. No manual tuning required. This approach also ensures that constraints are satisfied. Component 2. Hybrid optimization. We combine particle swarm optimization for global exploration with mimetic algorithms that add local BFGS refinement, balancing exploration and exploitation. We take best of both worlds. Component 3. Neural network surrogate. A deep sets architecture, chosen for permutation invariance, approximates the expensive objective function. Active learning periodically adds high uncertainty points to improve accuracy. Together, these components achieve 80 to 90% computational speedup while ensuring zero constraint violations. Traditional penalty methods work like this. You have your objective function, the coverage area A, minus a penalty term. The penalty term is rho times V, where V counts how many constraint violations you have. The problem is choosing rho. Too small and constraints are ignored. Too large and optimization gets stuck. Our solution treats rho as just another variable to optimize. Instead of optimizing z alone, the positions and rotations, we optimize zeta, which includes both z and rho together. Now, the question becomes, how do we know what rho should be? Here's where the neural network comes in. We train it on examples of zeta paired with their objective values. The network learns when violations are high, rho should increase. When optimization stalls without violations, rho can decrease slightly. The network predicts both the objective value and how sensitive it is to changes in rho. During optimization, the algorithm automatically adjusts RHO based on the network's guidance. If violations exceed 0.01, increase rho. If we're stuck, try reducing it. The result? 0 violations across all experiments without any manual tuning. For computational acceleration, we use a deep sets architecture ensuring permutation invariance. Coverage shouldn't depend on object ordering. The architecture has 3 stages. Per object embedding layers, process each object's position and rotation, mean pooling creates a fixed size representation, and output layers predict the objective value. We train on 5,000 to 10,000 samples using a multi-fidelity strategy. Monte Carlo approximation with 3,000 points for 80% of evaluations during exploration, and exact Shapley computation for top 10% candidates in validation. Active learning, every 50 iterations, identifies high uncertainty points, evaluates them exactly, and retrains the network. This achieves RMSE below 0.005, with inference at 1 millisecond versus 1 to 5 seconds for exact evaluation, a 10,000 to 5,000 times speedup per evaluation. We implemented 2 meta-heuristics. Particle swarm optimization uses 50 to 300 particles with velocities balancing inertia, personal best, and global best positions. Our mimetic algorithm enhances evolutionary search with local BFGS optimization applied to 35% of individuals. This fine-tunes promising solutions. Both algorithms use the neural surrogate for 80 to 85% of evaluations, reserving exact computations for elite individuals and validation. The mimetic algorithm consistently outperformed PSO by 3 to 5 percentage points, because local refinement can squeeze additional coverage from good configurations by fine-tuning rotations and positions. We tested on a challenging instance, a 10-vertex irregular polygon with 330.4 square units area, covered by 20 ellipses whose total area exactly matches the polygon, making perfect coverage theoretically possible. We added 6 circular restricted zones strategically placed to complicate coverage. This creates a 60-dimensional optimization problem. With a 10-minute time budget on a standard 8-core CPU, PSO achieved 90% coverage, 298.15 square units, and mimetic algorithm reached 94% coverage, 311.97 square units, both with 0 constraint violations. The neural surrogate, trained on 600 samples, provided 80% computational reduction. Without it, achieving similar coverage would require 50 to 60 minutes. The visualization confirms correctness. Ellipse poles avoid red restricted zones, coverage overlaps these zones as intended, and minimal uncovered area remains in corners where ellipse geometry prevents coverage. The 94% result is near the practical upper bound given geometric constraints. Why didn't we reach perfect coverage? 3 geometric factors create fundamental limits. Ellipses cannot perfectly tile irregular polygons. There will always be gaps. Restricted zones create spatial bottlenecks limiting feasible placements, and overlaps between objects, while sometimes necessary, reduce effective coverage area. Our 90 to 94% coverage approaches the practical maximum for this configuration. Further improvements would require either different object shapes, relaxed constraints, or significantly more computational time. Our contributions are threefold. We introduced neural network-guided adaptive penalties that eliminate manual tuning while ensuring 0 violations. We demonstrated deep-set surrogates with active learning achieve 80 to 90% speedup for geometric optimization, and we showed hybrid mimetic algorithms reach near optimal coverage in practical timeframes. This work immediately applies to telecommunications network design, crisis response planning for mobile health units, and environmental sensor deployment. Each requires rapid optimization under real-world constraints. Future directions include extending to 3D coverage, incorporating uncertainty in demand or zone boundaries, multi-objective optimization balancing coverage with cost, and online adaptation for dynamic environments. This research demonstrates how modern AI techniques enhance classical optimization for complex real-world problems. Thank you for your attention.